I think the whole world has turned to that methodology. And I was on one yesterday where the 500 people who could actually post questions was filled, and then they had to go live stream on YouTube, just like you are as well.
Wow. Who were you, the speaker?
The whole world has turned.
So let's get started. Welcome everyone to the Earth to Earth seminar. Thank you for joining us today on the 28th of January. As a reminder, the mission of Earth to Earth is to engage the UK geoscience community with inspiring science from internationally leading researchers while promoting inclusivity and diversity and supporting the advancement of early career researchers and highlighting geoscientists' contributions to addressing global environmental challenges. And again, if any UK institution would like to be involved, please just reach out to us. So on the technical side for questions today, we're going to be using the Q&A, so you can drop a question in at any time and we'll come to them in the end, at the end of the talks, where we'll pitch the questions to Lindy and Rona. Now it's my great pleasure to introduce today's co-speakers. We're very fortunate to be joined by Professor Lindy Elkins-Tanton from Arizona State University and Dr. Rona Oran from MIT. Rona gained her PhD at the University of Michigan before moving to MIT to work first as a postdoctoral scientist and then taking a position as a research scientist working on NASA's Psyche mission. Rona's work investigates planetary magnetism, plasma physics, and the space exploration of asteroids and moons, specializing in computational modeling of the plasma environment around planetary bodies and spacecraft, which, as well as enabling successful space missions, Rona's applied to investigate magnetism on the moon as well. Lindy is the managing director and co-chair of the ASU Interplanetary Initiative and the PI of the Psyche mission, NASA's 14th Discovery program. Lindy's research has investigated terrestrial planet formation and evolution, from the birth as magma oceans to subsequent growth of atmospheres. And Lindy's received many recognitions of her scientific leadership, including being made an AGU Fellow, member of the American Academy of Arts and Sciences, and in 2020 was awarded the National Academy of Sciences Arthur Day Prize in Lectureship. So thank you so much both for joining us. Today, Rona and Lindy are going to be talking about Psyche, Journey to a Metallic World. So I'll hand over to you now. Thank you.
Thank you so much. I'm so excited to be here, and I know Rona is too, and so thanks so much for the invitation. I'm now sharing my screen so I can get this going in its proper way. Excellent. All right, I'm starting out with my cover photo is my finger pointing at tracks of some quail out in the desert here in Arizona, because I'm not going to give a straight up science talk here. I want to start a little bit with a topic of teaming in science and how the science community works. It seems particularly apt in this year of concern about diversity and inclusion. And it's something, how teams work is extremely important to me. And I want to talk about it because it's been central to the Psyche mission. And so I like this Jonas Salk quote at the bottom, that the object is not to put down the other, but to raise up the other. And so most of academia, I would argue, is built on the hero model. This is certainly what I experienced through all my training at MIT. Fantastic place, which I love and have deep roots and connections with. This has worked beautifully for a millennia. This is the model where one person owns their subfield at a given institution and they control a mountain of whatever size of people and resources. There are many benefits to this model. It has brought us much of the knowledge that we have, but there are also problems with it too that I just say are large problems. One is that in certain circumstances, depending on who the hero is, progress can become incremental. Knowledge can just be added like little slices at the bottom of the mountain until it bumps into the next mountain, because so much of what we do is based on competition. And so the question is, how do we break out of the incremental progress model and work toward the really big goals that we all need to do as an interdisciplinary group? And the second problem with the hero model, of course, is culture. The hero culture is not necessarily inclusive, just, or even safe for anyone but the hero. And so it's not that I feel that we need to abandon this, but I think we need to examine it. And that's what I've been spending a lot of my career doing, particularly once I was in leadership positions. And so why positive team culture matters. I do feel like I need to actually address this directly. And I imagine that the people who are listening to me right now are having a sort of a range of different emotional responses to what I'm saying. And it's interesting because at one point when I was a graduate student at MIT, and then again when I was faculty, I'm kind of picking on MIT right now because it was my like formative thinking around this. It was implied that if we needed to talk about positive team culture, it meant that we were weak, actually, because if you were really tough enough to make it, then you didn't really need to talk about being nice to each other. And it's certainly not the case everywhere, but there is some of that in academia, and I know that everyone has experienced this a little bit. And so, but there are so many reasons why it really, really matters, why it's important to actually pay attention to. And one of them is you make better decisions on group decisions if more ideas are heard and cool heads think better. I've had people tell me in aerospace that the best decisions about space mission hardware are made when people can stand up and scream at each other and pound on the table, and that's the way you get to the truth. And I think that's a really great way to silence people who have parts of the truth. And so thinking about that. And then project risk is actually reduced. We have a motto on Psyche mission that our standing review board really loves. The best news is bad news brought early. And that is only possible when people aren't afraid of each other, when people are willing to speak up what they notice as being a problem. And that has given me the ability to actually stand up and say that a positive, inclusive team culture where people's voices are heard isn't a luxury. It's actually worth $1 billion because it helped us to win this mission. NASA headquarters told us explicitly that one of the reasons they were happy to select us for flight was that they could see that our team listened to each other and that people passed the questions to the person who was actually the expert instead of attempting to answer themselves, and so forth, things like that. So it really does matter. And also attraction and retention of talent. Of course, bullying, rudeness, and harassment reduce diversity. The social science shows that if you feel that you don't have a group of people that are like yourself in whatever way you identify, then you feel alone. And if you feel alone, you're most likely to leave when there's a bad culture. And it takes about 25% of people like yourself before you stop feeling alone. And so it's really hard to reach that. You can have every hiring rubric you want in the world, but if you don't have a way for people to stay because of the culture, because they feel alone, you're never going to have a diverse team. And so I'm a huge proponent of having every single person's voice heard and everyone to rise on the merits, no matter what their sex, gender, race, ethnic, whatever characteristic it is. And so this is not a matter of dividing and raising up one part. It's a matter of making it equal for everyone. So where did we start on this attempt to put together a successful team? This was back in 2011, a paper that I wrote with Ben Weiss and Maria Zuber about the concept of partial differentiation. That in these planetesimals, these little bodies that formed sometimes in less than 100,000 years after the first solids in our solar system, formed very fast up to bodies that were tens or hundreds of kilometers in radius. That they might, some of them have melted on the inside and differentiated into a metal core and a rocky layer, but then retained an unmelted rind on the outside. And that could explain the origin of some primitive unmelted meteorites coming from the same body that had a core magnetic dynamo from its internal differentiation. And it was a very, at the time, kind of incendiary paper. We had the exciting experience of standing up to give our talks, Ben's on the samples he measured and mine on this modeling paper at the Lunar and Planetary Science Conference, and having people lined up several deep at the microphones before we started speaking because they were so ready to rebut us. That's always a good sign. You can have a good conversation. And what happened was I got an email from a couple of scientists at Jet Propulsion Laboratory asking me, would I be interested in working with them to propose a mission to test our hypothesis? And that is how this started. I did not start out looking for a way to be the PI of a mission. It never actually occurred to me that that was a path that was available to me. And this is how it started. And so this was our timeline. Back in 2011, Jet Propulsion Laboratory contacted me and also Eric Asfog, and we quickly brought in Ben, and then we had a group of 5 and a couple of other people. And for 2 years, we worked on the development between 2011 and 2013. Now, when the announcement of opportunity comes out for a really big proposal like this, you'd better have pretty much written your proposal, because there is not enough time between the announcement and the due date, a number of months, to write the proposal. And so that's really what we spent doing those 3 years, convincing Jet Propulsion Laboratory to be our partner, going through intensive programs to figure out what we were going to measure. Where we wanted to go was the first question. We didn't start with a target. We started with the science question. And then we figured out we wanted to go to Psyche. And so this was the process of going through proposals. There are 2 steps. The first, step 1 proposal, 28 proposals went in. They were each about 250 pages long. We had a team of 50 people writing them. This is all volunteer. You have to do all of this in your copious spare time. And then we won. In 2015, we were one of 5 missions down selected for step 2. Then they gave us $3 million to write the step 2 proposal, which is more money than I'd ever had to do science before. And this wasn't even for science. This was to write the proposal. And my friend David O, who's our lead systems engineer, and I looked at each other and we thought, we're rich. We can do every test we want. We can build all these engineering models. And then JPL turned to us and said, actually, it's not enough. You need 5 million. You know, we'll kick in, Maxar will kick in, we'll figure this out. $5 million to write the step 2 proposal, 1,000 pages, 150 people on the team. And then in 2017, we were selected for flight. And this is as short a process as you could ever hope. Normally, you'd have to go through this 2 or 3 times and then often never be selected. So we're very, very lucky to have gotten through it in this amount of time. But it's interesting because how many of us know what we're going to be doing for the next 30 years without a doubt? It's quite a moment. So what is Psyche? So we have some hypotheses. One of them is the picture behind me, behind my head right now. Here's our fiducial hypothesis, our main idea of what Psyche is. So we think that there was a melted differentiated planetesimal, the one on the left. So it heated to the point that its rock part and its metal part melted. This would have been in the first probably much less than 1 million years of the solar system. Now that our understanding of what's called pebble accretion has grown, I think we understand that this could even happen in tens of thousands of years. So I use the word achondritic, meaning that it's melted out all of its little meteoritic chondrules, the textures of chondrules. And that it froze maybe with a low iron rock near the core and the higher iron near the surface. This becomes important because of the data we have of Psyche right now. The one thing that seems fairly clear is that its rock fraction does not have very much iron in it at all. So there's almost no evidence in the spectra from Psyche of iron and oxygen bonds. And so even though we think it has a rock fraction, that rock fraction has to be very poor in iron, which is a trick. How do you do that? And so then our idea is that impacts would have stripped the outer higher iron rock away and left a lower iron rock and a mainly metal core. That would match the density measurements we have and the spectral measurements that we have. Maybe it could be sort of a palissitic core mantle boundary or even a CB chondrite, if that means anything to you. Kind of parent body is actually extremely, right now, fits the Psyche data, which is kind of amazing. And although I'm going to say this once and I'll probably say it again, almost everything I tell you today is almost certain to be wrong. And when we get there, we're going to find out it's quite something different. I'm just telling you the best things that we know right now. So this is science in action. Here I am telling you the best data-driven ideas that we have, almost certain to be wrong. The other option, which is really interesting, is it could be chondritic, meaning primitive, unmelted material from the beginning of the solar system, if there is a way to make it very high metal and very low iron rock. And one way to do that is if it formed very close to the sun and was reduced by the heat of the sun so that the iron would be in the metal form instead of in the oxide form. We really do not have samples of this material, but it has been hypothesized to be something that could form. And so now you see the kind of teetery outer edge of the delicate branches of the tree of knowledge that we're trying to balance on right now, because basically we have to choose between an unlikely hypothesis and an almost impossible hypothesis. And of course, any of these could have been made into rubble piles as well. This is based on the data we have from Earth. So who knows, but that's where we are. So keep your scorecard and get ready to cross these all off when we find out what it really is. So now you see, this was the idea, this was the cover of that concept study report, that 1,000-page document. We hired a professional Hollywood artist. This is the kind of thing you can do with these budgets. And he made this beautiful work of art for us, which you can see is sort of 30 seconds after a giant stripping impact. And you can see you can see like the liquid metal core beginning to be revealed from within the shrouds of rock being stripped away. So that was the concept. And this is another artist concept from the same wonderful artist, Peter Rubin, trying to imagine what a metallic and rock asteroid might look like. Maybe it had sulfur volcanism up under the surface, and we'd have areas of the surface that are made of troilite. Would the craters have kind of prongs and other bits that froze because they're metal instead of rock? Totally a guess, based on good science, but totally a guess, because here's what Psyche looks like. This is what we know of it. This is a picture actually from a telescope in my backyard. But even through, for example, the Mount Wilson 60-inch, it doesn't look very different than that. It just looks like a tiny dot. It's a very far away asteroid. And we have no images, humankind has no images of metallic asteroids. We do not know what this looks like. And so that's important to stress. What we do have is we have got some very nice radar reflective, a lot of it from Arecibo, amazing Arecibo. Combine radar bounces. Can you even believe that we can send radar from Earth to an asteroid at 3 AU and receive the bounce back well enough to actually begin to create a shape model as it rotates? I mean, that blows my mind. We put that together with the light curve and you get a shape model. So we do have a pretty good idea of the shape. There are, say, 4 good teams that have done shapes for Psyche, and they do not agree, but they don't disagree wildly. And so we do pretty much know about how big it is and what its shape is. And this is how big it is. If you were to plonk it down on top of Switzerland, which I promise we will not do, parts of Switzerland would still stick out. So as an asteroid goes, it's really quite a big one. It's about the size of the state of Massachusetts, where many of us have spent so much time. If we had it here in Arizona, where I am right now, it would reach almost from Phoenix to Flagstaff, not even all the way across Arizona, which is a big place. All right, and so that was the bit I talked about before. The first discussion, the announcement of opportunity is released, the step 1, step 2, followed by this amazing site visit where NASA sends out their professional review team and they grill you after a week of living together in hotels and answering questions. It's unbelievable. It's like your qualifying exam for your PhD on steroids as a Hollywood super production. It's something else. Love to talk about that at length another time because it's something else. So now we, after selection, we go through phase B, which is formulation. We have our giant preliminary design review. And then the huge critical design review we went through. We were the first major space mission, I believe, ever on Earth to do a virtual critical design review. That's usually 5 days in the room with 150 people. And we did it virtually, and we had a really, really good outcome in that the review board was able to be really engaged, learn everything they needed to learn, discover all of our risks, help us with our challenges. It was very successful. So we are now here in phase C and D. We are about to enter phase D. I think there will be a press release about that next week. So stay tuned. We've been going through some big reviews this week. In fact, today, as soon as we're finished here, I'm going to go back to the launch vehicle preliminary design review with SpaceX, where we're reviewing how we get our rocket ready to launch us. So launch in August of 2022. Despite COVID, we're on a good path to make this. Our schedule is what we call brittle. That is to say, we can't take too many more hardware slips because COVID shutdowns for hardware building have caused slips, but we're still on track to make it. I'm really proud. It goes back to the team. Not every team is weathering COVID as well. And I'm very, very lucky to work with the team that we do. And so then we will launch, we'll do a Mars flyby for a gravity assist, and we'll arrive at Psyche in 2026. That's our plan. We've got 3 science goals: to understand a previously unexplored building block of planet formation, to look inside the terrestrial planets, including Earth, by directly examining the interior of a differentiated body, which otherwise can't be seen. If Psyche is a part of a differentiated core, which we think it is, but as I said, who knows? then indeed this is really the only way humans will ever see a core, because we're never going to ours or the core of any of the other planets. I would posit with some confidence that that is never going to be an economic feat, no matter if the technology exists, that's going to be worthwhile to do. And then to explore a new type of world for the very first time. Humans have never gone to a world made mostly of metal, a metallic world, so a new kind of exploration. And we're taking multispectral imagers and magnetometers, which you'll learn more about in a minute, and the gamma ray and neutron spectrometer, which is a quite astonishing piece of equipment if you're not familiar with it. It actually receives the secondary products of cosmic rays striking the surface of Psyche, the secondary products of those strikes of cosmic rays being gamma rays and neutrons, and by measuring their energy, know what atom had been struck. So we can actually determine the atomic composition of the surface of Psyche by measuring its gamma rays and neutrons. This is what the spacecraft's going to look like when the beautiful giant 20 kilowatt solar rays are unfurled. The size of a singles tennis court is what it is in the end. And we're going to be launched on a SpaceX Falcon Heavy rocket like this one. And they are intending to land the boosters, so it should be a pretty dramatic happening. And we're just starting right now. It's 18 months away. Every single second is planned between now and then. I'm already at my total limit for workload and planning to offload things so that I can really attend even closer during this next 18 months, because it's probably going to be the most intensive work period of my life. I'm really looking forward to it. It's going to be amazing to learn how this all happens, culminating with this. And we're working on ways to allow everyone in the world to be involved if you're interested. So finally, just a note, this is a picture of the team from that site visit during the step 2. This is just a part of the team that was there living in Palo Alto for a week for the site visit. We've got a Twitter account. I have a Twitter account. We've got a great website at ASU with all the information about the mission. And finally, just a little message that I like to share. If you don't object to this kind of thing, it's usually my ending slide when I give talks like this. Just a suggestion about how much success can be attained by being bold and also by being kind, which is not something I think we talk about enough. Thank you very much. I'm going to turn it over to Rona now.
Hi, can you see my screen? Is it working? Great, okay. So thank you, Lindy, and thank you for the organizer for inviting me and giving me the opportunity to speak in this seminar. I'm very excited about that. So I'm Rona Oran. I'm from MIT, from the other Cambridge over in the US. And I'm part of the magnetometry investigation team with Ben Weiss and Jody Ream and Clara Morell, which I think she's in the audience. She's a grad student in our group, and she's also involved in Psyche. So this is the slide from Lindy showing you the timeline of the mission. So I joined the mission around towards the beginning, before the middle of phase B. And I joined the magnetometry team. And the first time I really heard about the Psyche mission was after that famous site visit. We're going to tackle the questions of whether or not Psyche is a metallic, as the metallic asteroid actually are stripped cores that survive the planet destruction from the point of view of magnetic fields. So we know several bodies in the solar system, like the Earth and Mercury, have magnetic fields, the terrestrial planets. We have indication that the Moon and Mars used to have magnetic field generated in their cores. So then this question of whether or not Psyche is a core is also related to the fact that cores tend to generate magnetic fields if they are metallic cores and that have molten metals in them. So if you can imagine a core like that being exposed to space after such a collision, then the red part here signifies this metallic core churning and creating a dynamo field, while the outer layers are exposed to space, they cool off and they crystallize. So while they stop generating a magnetic field, when they do that, they can record the magnetic field that is still being generated in the inside. So they can give us basically like a timeline of the magnetic field that's being generated outside. And this is part of the field of paleomagnetism that several here in the audience are related to, and the paleomagnetism lab that I am related to at MIT with Ben Weiss are actually experts in taking these magnetic fields and being able to tell what magnetic fields were existed in space on many different bodies, and actually say this existed 1 billion years ago or 4 billion years ago, all the way back to the beginning of the solar system. So the Psyche mission is really an exciting opportunity to go and explore a body like that with a magnetometer flowing around it. And I have here this artist conception Psyche, 3D printed, and the website that Lindy showed you will have this 3D printing file so you can do it yourself. So we're basically going to send a spacecraft that is going to orbit this body for around 1.5 years, but you cannot see magnetic fields. Magnetic fields are only measured, and so we need to be able to measure them and be able to characterize whether or not Psyche was magnetized. And there are many, many different scenarios of magnetization. 2 examples here show a nice and orderly magnetic field, like the Earth has a nice magnetic pole, north to south, whatever north to south is on Psyche. Or it can be very jumbled, maybe because it broke apart and came back together. So we are actually set up to find the first asteroid magnetosphere. And our task is to detect it, measure it, and map it. So how do you tackle a question like that? The first thing that we know is that we don't know if asteroids, have never been an asteroid that had a magnetic field that we measured from orbit. So this is an artist's conception of different planetesimals. And as Lindy told you about the partial differentiation, we may have, asteroids were largely not believed to have dynamo fields because of how small they are. But if they are partially differentiated, they may hold this secret within them. But so far, all the asteroids we visited by spacecraft did not have a magnetic field. However, the asteroids we visited were largely rocky. So even though they have some metal in their minerals, they are basically rocks. And here's a picture of Ryugu. And this is a close-up of Bennu that we just got a sample return from it. So it's really just a bunch of stones, a very familiar landscape. On the other hand, metallic asteroids, as Lindy told you very beautifully, we don't know what they are or don't know what they look like, but some clues that we may have is a hypothesis that iron meteorites that land here on Earth actually come from metallic asteroids, or at least from some layers within them. And if you look at an iron meteorite, it's very smooth. It's a very, very condensed piece of metal. There's almost like nothing there but metal. And it's very, very heavy. And here I am trying to move one at the University of California, LA. This thing is not attached to the table, and I'm using all my body weight, and it doesn't even budge. So this thing is very, very different from anything you would see coming from just the Earth's crust. And another beautiful thing about iron meteorites is that they have very strong magnetization that is being measured in our lab and in other labs around the world. And shout out to Clara that is measuring iron meteorites as we speak. So these are basically magnets from space, and they record the magnetic fields in space. So now if you want to plan for the mission of measuring a magnetic field of an asteroid that maybe is made of the same types of materials, you can use the information that we have about the magnetic field that they carry per unit weight, per unit mass, and say, what would happen if you extrapolate this to an asteroid that is the size of Massachusetts? And we use computer simulations or computer models to do that. We basically place some strange magnetic field and we place it in space. So space is actually not empty. It is filled with the solar wind, which is electrons and protons mostly, which are themselves a conducting fluid, and they carry a magnetic field, the magnetic field of the sun, which we call the interplanetary magnetic field. And then that magnetic field interacts with whatever magnetic field you have here on Earth. And if we stop this movie over here, oops, stop. You can see this region that is kind of dominated by the magnetic field of the body, while if you look here on the right, this is the undisturbed solar wind magnetic field, or the background field. So you can see that as you get closer to the body, you start seeing something that is very different. And this is what we call a magnetosphere. The magnetospheres are usually very, very big. The magnetosphere of the Earth is tens of thousands of kilometers. The magnetosphere of Jupiter is almost as big as the distance between the Sun and the Earth. But an asteroid magnetosphere is going to be only a few asteroid radii, and it's not that big. So how do you plan to measure the unknown? Basically, that was just one scenario, and we don't really know how it's going to look like. Are we going to be sensitive enough? The instrument's going to be sensitive enough? Are we going to have enough data to be able to tell apart this field from whatever is around it? So the first thing that we don't know is we don't know how strong the field would be. So here I'm showing the simulation of a Psyche that is very, very, very weakly magnetized. And you can see the background field is disturbed very, very close to the body. But then because it's a computer, we can do whatever we want, and we crank up the magnetic field, and you slowly get like this larger and larger bubble, the larger and larger magnetosphere. So if you're inside this magnetosphere, you're like, okay, I cannot see magnetic fields. I cannot, you know, for an imager, you can always see the body, but for the magnetic field, if you're not inside this region that is dominated by the body's magnetic field, if you're somewhere here, you basically don't know there is a magnetic field there. So the question for the mission would be, how close do we need to be in order to detect the magnetic field? Are science orbit that are planned by the mission going to be able to peer through this structure? The other question is that Psyche is itself rotating. It has a 4-hour day. And while it's rotating, this whole magnetic field that it has is going to rotate with it. So your spacecraft is basically moving around in a single point at each time, but this whole thing is moving as well. So how do you tease out all of these changes and figure out which ones of them come from the body? And then here I'm showing two simulations that show what happens when the Psyche rotates, imagining it has a magnetic axis that is tilted this way. So this is the rotation that you see. And the colors signify the magnetic field strengths, where green is just like the background solar wind field. So if you measure a green field, not very impressive. If you measure a blue or a red field, they are in a direction that we don't expect to see if only the solar wind was there, or if Psyche was there and was not magnetized. So that kind of gives us an indication of that there is a magnetic field that is associated with the body. And you can see this bubble, this translucent gray bubble that gives us the environment that is mostly dominated by the magnetic field of the body. But what this demonstrates is that this magnetosphere is going to change the whole time while the body is rotating. And it's also going to change if we change this IMF, this interplanetary magnetic field that we have. And the sun, as maybe you've heard about solar storms, and the sun is a very turbulent creature, and the solar wind is also turbulent. So the magnetic field, it keeps rotating. So we have a lot of uncertainty. And just to make it even more impressive how much uncertainty, these are 6 of hundreds of scenarios that we've been exploring of like, we don't know where the magnetic field of Psyche will be pointing at. And each of these pointings will give you a completely different 3D structure. And those are these black field lines. And I'm showing you mostly the field lines and not these bubbles, because the field lines are the ones that gives us the most hope, because it's these weird shapes and weird topologies that are going to really assist us and giving us clues of what a magnetic field is. Because simulations are great. They show you this nice picture of what the magnetic field is everywhere. You can rotate them, you can look around. But Psyche is actually constrained to a single trajectory, and you're not going to see the full picture. You kind of have to like construct it ourselves. So how do we plan for the unknown? We do this with the team. And here I'm showing, here is Ben Weiss, the lead of the magnetometry investigation, and Joe Durim, and here myself. This is Nora Allange, and she's working with us as part of the science operation teams. And she's JPL, and she connects us with so many people. And we really learn a lot about how to work with the navigation team, mission planners, mission scenario planners, thinking about when is the best time to measure things. Oh, we're gonna, like, the thrusters are gonna shoot out because we have an ion thruster, it's going to interfere with the magnetic measurements. So really thinking about how it all fits together is really, really important. Deborah Bass, so many people that work, so to speak, behind the scenes, but they're really so central to everything that's happening. And really going back to what Lindy said about teams and being able to speak and ask questions and being ignorant about what we're talking about. And here we are about a year ago, just before COVID started at Maxar with Psyche's cylinder behind us and part of the chassis being built. And here I'm just going to show you the culmination of a lot of these studies that we do and looking at different scenarios. So this is a simulation of Psyche, which is this the gray sphere in the center, and we have the bubble that signifies the magnetosphere. And then here is the trajectory of Psyche. And I'm coloring it by the size of the magnetic field that our would-be magnetometer would measure. And we just let it go through its orbit. I'm only showing part of the orbit and the closest one. But you can see we're like going around this bagel around the body, and each time we're measuring different part of the body and a different part of the magnetic field, and the magnetic field is changing. And red means 10 nanotesla, which is about 5 times stronger than the solar wind magnetic field. So it's a strong field, clear indication that something is different there. But we can have 10 nanotesla magnetic field in space just because of the sun. So it's really important to do this analysis carefully. So if you take this bagel and spread it out over a map of the magnetic field, this is laid out at longitude and latitude. You can see these clear patterns where the field is very, very strong, but you can also see how these strong fields kind of like step over each other because the field keeps changing. And every time you visit the same spot, you might measure something different. So what we do in the investigation is basically planning all the tools, all the software, all the algorithms, all the thinking, simulations to plan for that. So when we get there, we kind of have everything we need in our toolkit to be able to tease out the noise from the patterns and find out if Psyche was magnetized or not. And that is it for me. I also have an inspirational slide. I actually have this on my fridge. This is, I got this at AGU once, and I love this from the Apollo era, seeing Earth from the moon and how you can always change your perspective.
Thank you so much, Rona and Lindy, for your talks. Really inspiring science and inspiring thoughts on how to do science as well. So really appreciated that. Thank you. Just a reminder, any questions can go into the Q&A box. There's a couple there already, and then we can pitch them to Lindy and Rona and get the answers. So I'll start with one question that's come up about the kind of target selection. So how many objects were considered before Psyche was settled upon? And were there others that we perhaps knew more about that were also tempting targets?
That's a great question. We really wanted to visit something that was differentiated, and Ceres and Vesta visited. And so what was there that could really help us understand the core in a unique way? Our ideal scenario, something that we searched for some time, was a recently disrupted family of asteroids that had come from a single differentiated parent that had been struck and broken. Because you may know that there are families of asteroids that can be shown from their orbits and their relationship to have come from a single parent. And so you know that they were all parts of that parent. At the time, there were none that were for sure from a differentiated parent where you could look at the spectra of the pieces and say, well, that one's definitely flat and metallic looking, and this one has all these lovely bumps in its spectra showing that it's very rocky. So first, that was a problem. We couldn't find one where we could definitely say it had a core and exterior. But then also, surprise, space is really big. And it turns out that even going to a family, trying to get from one to the next was almost impossible. And so we really had to abandon that plan. And then definitely our next best bet was Psyche. There are about 9 so-called M-class asteroids that are thought to be made of metal. We don't really know for sure, but thought to be made of metal. Psyche is the only really large equant one, so 225 kilometers diameter for its equivalent sphere. It's kind of potato shaped, as people say. Cleopatra is the next one that's big. It's about 50 kilometers, but it's shaped very long and narrow like a dog bone. It's tempting to think that it was a piece of liquid that got spewed out from a core and was tumbling, and so you get its bond number would indicate it would sort of freeze in space like a dumbbell, but we don't know. But so definitely Psyche was the best second choice.
Fantastic, thank you. Another question here. Could the impact that stripped Psyche of its rocks, so this idea, I guess that fantastic art that you showed, suggested high temperatures, and could they have influenced the magnetic field that's now preserved on the body?
Yeah, I think I should take that one too. And Rona, you may have something to add, I don't know, but first of all, it looks like, and this is work of Eric Asfog, it looks like that in order to strip most of the rock from a metal core of a planetesimal would take between 4 and 11 impacts. You can't do it with just one. And so either Psyche, if it's metal from a core, could be a droplet from a much bigger impact, like Mars-sized bodies, or it could be a stripped planetesimal, which would take 4 to 8 impacts. The thing about the planetesimal impacts is that they don't melt the impactor. There just isn't enough energy. You don't get impact melting until they're much bigger bodies. And so Psyche would have had to have been molten already when it was being impacted, so it would therefore not have magnetic field recorded at that time. And so then we'd be looking at a dynamo and recording of the magnetic field while it cooled after the stripping impacts.
Fantastic. Got a question from Richard Harrison. It's Rona, can you comment on your take on the debate around the strength of the solar wind field and recent suggestions that these fields could be responsible for the magnetization of some chondritic parent bodies?
Yes, sure. I'll be happy to address this. So actually, the way I kind of transitioned into this field, that my first work on asteroids was to think about this problem of partial differentiation. Like this relates to partial differentiation. If the magnetic field that we see in chondritic meteorites comes from the solar wind, then you don't need to partial differentiation and a metallic core, a dynamo core to explain them. But the solar wind, as I showed you in the simulation, it's constantly changing. And its direction changes all the time. And over time, if you average it even over the solar cycle, which is 11 years, you're going to get something that's 1% on average of the vector average of the magnetic field. So you can imagine you have the asteroid and the solar wind is coming, induces a magnetic field this way, and then an hour later it induces a magnetic field this way, and then these fields basically cancel each other out in the interior, and you're only going to get about 1% of that field if you average over many, many years, and let alone millions of years or thousands of millions of years of cooling time of chondrites. Another issue is that chondrites, if they are undifferentiated bodies, they don't have metallic cores, they don't have magnetic fields, then they are very, very weak obstacles to the solar wind. So the solar wind is basically going to flow. The magnetic field of the solar wind is going to basically flow through them, just as it doesn't for the moon. So if you take measurements around the moon, you're not going to see any pileup or amplification of the solar wind. It just, because the body is so resistive, the magnetic fields can penetrate through it, they diffuse through it. So just like as a crash course, conductors don't like magnetic fields coming into them. Resistors let magnetic fields come into them. So if it's a very rocky, non-metallic, non-conducting body, it's not going to really make an impact, that much of an impact on the solar wind magnetic field. The interaction is going to be very, very weak. And on top of that, the magnetic field of the solar wind keeps changing and the body is rotating and everything is happening. So we think that the average, we actually had a paper about this, that the average magnetic field that you actually record over the cooling time of the acquisition is going to be very, very weak, several orders of magnitude below what you see in chondrites like Allende.
Cool, thank you. Question from Rich. How does the radius of the orbit affect the ability to sense a field? Would a geodynamo produce a field that could definitely be sensed from the planned orbital radius?
I don't know if Rona could hear you. I couldn't quite hear you.
Yeah, I couldn't hear it so well.
Could you
sorry.
repeat again?
Yeah, how does the radius of the orbit affect the ability to sense a field? Would a geodynamo produce a field that could definitely be sensed from the planned radius of orbit?
You mean the orbit of the spacecraft?
Yeah,
Yeah, I
around.
think he's talking about the orbit of the spacecraft. And so, Rona, would you like to talk about our step-down orbit strategy?
Yeah, so there's going to be 4 orbits, and we're going to slowly get closer to the body. And in each of the orbits, we're going to achieve another science objective by the different instruments. For the magnetic field specifically, we think we're going to be able to make a determination of whether or not Psyche is magnetized up to some minimum level from orbit C, the 3rd orbit, so 2nd orbit from the ground, basically. I didn't hear everything you asked, so I'm hoping that I answered the question.
Oh, sorry, yeah, no, that's great. Thank you.
Okay.
A question on the Q&A. It looks like Psyche has about 1/3 the radius of the moon's core. Is there any way to put bounds on how big the unstripped body might have been?
Yeah, this is something that I'm thinking about very hard. And the short answer is no, there is not. But imagine that it is large sections of metal, implying that it was a differentiated body. So not finely mixed or intimately mixed, but large sections of metal plus rock. If the rock really has almost no iron in it, if it's very low magnesium, the only way that I know, and maybe people it's seriously, like every time I give a science talk to a science audience, if you can think of another way to make a body that matches the spectra and the density, I would love to know about it. Like, we're collecting ideas and there are not very many. So the only way I know of to really separate the high iron rock from high magnesium rock, which is kind of your option. You're going to trade off iron or magnesium in that crystal site for all of those popular mantle minerals. The way to separate them is through fractional solidification. So the first bits that you solidify from a magma ocean, say molten planetesimal, will be very high magnesium, very low iron. That matches the spectra. And then as you continue to solidify, only the high iron material is left, which does not match the spectra. And so how do you get only the high magnesium? And it seems like there's 2 ways. One is by doing that fractional solidification process and then removing the high iron. Sounds clean and beautiful, but that fractional solidification process requires a very good gravity field and a fair amount of time to actually separate the mineral phases. And for a body the size of Vesta, say, or Ceres, which would be appropriately sized if Psyche was entirely a core, only the very first minerals to crystallize could possibly settle. So you'd get a very, very small layer of settled high magnesium material, and all the rest would basically batch solidify because there wouldn't be the gravity and the time to allow the minerals to separate, if that makes sense. So you can't really make Psyche from a body the size that would have Psyche as its core. You just couldn't make the differentiation of the minerals. So how big a body would you have to have a high magnesium, low iron rock layer that would be commensurate with Psyche's density, which seems to be about halfway between metal and rock? And so that's not quite answerable because it also depends on a stochastic process of stripping, which isn't perfectly predictable. But let's just say it would have to be big. I mean, it would have to be something like a fraction of the size of the moon in order to get to that kind of thing, or bigger. The other way to have a rock that has really virtually no iron oxide in it, if this is true, would be by starting from material that had no iron oxide, and that would require something that was very highly reduced. So those are the scenarios we've been able to think of, and they give us a bit of a constraint on size. Love to hear all your ideas, you clever people who have it right in your head right now. So send your ideas.
Thank you. It's a question from the YouTube stream. If chondrites with uniform paleomagnetism are thought to be the crust of partially differentiated parent bodies, what's the difference between the melting point and Curie temperature of chondrules?
Rona, do you want to take that one? I mean, presumably chondrules are not the source.
I don't know what the melting point of chondrule is. So
I mean, the silicates are going to melt, you know, 1200 and higher, depending on their composition, Celsius, and the Curie temperatures, depending on the mineral, are I don't remember exactly what they are. Richard certainly knows, Rona probably knows, but it's at least 500 degrees difference, right? But the chondrules themselves, and correct me if I'm wrong, but the chondrules themselves are mostly silicate and or glassy, so they will not be the recording mechanism, right? The recording mechanism would be some mineral phase that could actually record a magnetic field, which, Rona, what would that be? Can you, this is like your general exam. Can you like reel off what the recording phase is and its Curie temperature? Or we'll make Richard do it if you can't do it.
This is post-accretional magnetization. So it's not the magnetic field and the chondrules themselves. It's like so the chondrules can be magnetized by the nebula, and then when they accrete, that field is not going to be coherent. But if after accretion, you can remagnetize the entire body. So it's not actually, it could be the matrix between the chondrules, and it can be other minerals that formed around them. So the chondrules, like if you look at the Allende, there are chondrules there, but they're not the most of the mass there. So as far as I know, the paleomagnetic field that we measure from chondrites is not in the chondrules. And that field is the field that is supposedly generated by the core of the partially differentiated chondrite parent body.
Excellent, thanks. We have a question from Tamsin Maida, which she acknowledges maybe is perhaps an unfair one, but there are so many great questions here. Do you have a top discovery that you dream of the mission making above all else? Or the top three, if you can't narrow it down to just one?
I'm sorry, can you say one more time, Oliver? I'm having a little trouble hearing you, unfortunately.
Oh, apologies. So many great questions, but do you have a top discovery that you dream of the mission making above all else? Or possibly three if you can't narrow it down.
Oh, so I'll name one, and then Rona, do you have one also? And think about it. Well, maybe you do. So my dream is that Psyche is none of the things that I've just described, and that Psyche is some sort of super reduced, crazy original material that maybe accreted in the molten phase from the early protoplanetary disk, like something that changes our idea about how planets are made. So probably we'll go there, and it'll end up being a CB chondrite or something that will be quite amazing and fabulous, but kind of a little bit predicted. But what I really dream of is that it's nothing that we now think that it is. That's what I hope.
I think for me, coming from the field of space sciences, space physics, as like the plasma people of the world, I think for us, the discovery of asteroid magnetosphere would be a first, and it's a very exciting possibility. Because it's such a small body, and because it's going to be a very different creature from any magnetosphere we explored. And the idea that this magnetosphere is so, because of how like close in it is, of how much it's going to tell us about the body. So we're like really going to be able to take that magnetic field, and it's going to be like a wild magnetic field. That would be the most exciting for us, because then that I think would imply the most about the formation of Psyche and its history. And so I think that connection between the stuff that you see outside in the solar wind and being able to go not just inside the body, but like very, very far in history, I think that's like the most exciting thing. And yeah, I think the whole the different possibilities of what kind of body Psyche actually is also very exciting. And I think, of course, we would like to be able to measure magnetic fields. So.
I have to, before we go to the next question, I just have to add briefly onto this for context that what is the most exciting discovery. The thing is that since this is a category of solar system body that humans have never investigated before, it puts us in a really unusual circumstance. There aren't that many categories of bodies that we've never looked at, it's like the first time we went to Antarctica or the first time we went to the North Pole. People thought that there were holes in the North and South poles of our planet that led to the warm inside. They thought this into the 19th century. And that's why you could get something big like a polar bear living up where there's apparently only ice. So we really had no idea. And so this is something like that. We're going to a kind of place that no one's ever been before. In the proposal process with NASA, there's a table you're meant to write, which is the percentage improvement over existing measurements that your measurements will be. And ours were infinite, 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 because nobody had never measured any of these things before. And so to me, that's the thrill of it. We really do not know what we're going to find.
Cool, that's super exciting. Thank you. We have a question from James Poole, and this touches a little bit on something I was wondering about in terms of the relation to meteorites as well. Is it possible that Psyche is the parent body of some of the iron meteorites? And would it be possible to compare the magnitude of paleomagnetism in iron meteorites to the magnetic field measured on Psyche to make a link?
Yeah, let me start and then hand that to Rona. There's been a hypothesis for a long time that Psyche could be the parent body of the 4A iron meteorites, because if you're not up on dynamics, virtually all of the asteroids, meteorites that fall to our Earth today come from the asteroid belt. And so you look for what could be the parent body of something that's a big metallic body that had to be the parents of the 4As, and that's the kind of the candidate. The problem is that iron meteorite classes are categorized by trace elements that we are not going to be able to measure on the mission. So we will not be able to confirm that Psyche is the parent body of any meteorite family that we have, for sure. But as Rona can explain, we can compare the magnetic field.
Yeah, so a large part of what we did in simulating different scenarios was basically taking the magnetic field from paleomagnetism of iron meteorites and extrapolating it to a larger body, and making that assumption that you can just, like, if you just stuck all of those little meteorites together to the size of Psyche is not trivial assumption. So Clara Morel, which is, maybe she's still in the audience, she's been working actually on this problem of taking iron meteorites and then measuring larger and larger and larger iron meteorites and see if it actually carries over, if you have this connection between the paleomagnetism of the iron meteorites and the one from Psyche. I'm not sure what is the largest one they measured, but they actually went to the Museum of Natural History in DC and constructed a huge, like, magnetometer cage to cancel, a cage that cancels out the Earth's magnetic field, so it can actually measure the field that's coming from the meteorite. So you're kind of filling in the blanks. But then there's going to be a very big jump when we get to Psyche. So it'll be very, very interesting to see if it carries over or not.
Cool, absolutely. Got a question from Michael Carpenter, kind of focusing on the material properties now. So what is the temperature of Psyche at the moment? And do we know the properties of all the relevant minerals at these temperatures? And will the resolution of the data be sufficient to allow discrimination between mineral types?
Yeah, we hope so. So the temperature of Psyche right now is actually not precisely known. So you can make models of it, and we're doing that. There's a very, very talented postdoctoral scientist who's working with us, Carver Beerson, and he's made a fantastic 3D model of Psyche. Here are the challenges. We've got something like a temperature field of its surface from ALMA, and that's been done by a researcher at Caltech. Forgive me, her name is not coming to my mind. I wish I could immediately give her the attribution of her work. And then, but it's, low fidelity, and we don't know for sure, but you think like a largely metallic body in the outer asteroid belt, it's gonna be really cold. It has no internal heating, it's way too small for that. But here's where the question comes in. This is why it's an interesting question. Psyche's spin axis, which we usually think of as north-south, is knocked over into the ecliptic plane. So it's in what we sort of think of as rotisserie mode. So sometimes of the year, it's gonna, let's see, how do I get this? It's gonna be, its spin axis is gonna point right at the sun, and its pole will be quite hot. There we go. And then other parts of the year, it'll be parallel to the sun, exactly like Rona is showing. And then it'll get evenly heated all the way around like a rotisserie chicken. And so the question is, how efficiently does heat get transported from one part to the other? What is its thermal inertia? That depends so much on both the composition, the porosity, and the grain size of its surface. So you can measure thermal inertia, but it has too many dependent variables to be able to extricate them one from the next. We don't know the answers to composition, grain size, or porosity. So we're doing a whole range of different models to discover how important heat transfer from one end to the other might be. So I thought that was kind of an interesting piece of the science that we're doing in prep. But the other piece that I think is very interesting is Jay Milosh, rest in peace, amazing scientist and human being, came up to me a number of years ago and said, you know, when metal is very, very cold, if you strike it like with an impact, it will actually shatter like glass instead of behaving in a fluid or ductile manner the way we're used to with impact craters. So, for example, Psyche's south pole, when its north pole has been facing at the sun for a year because its orbital period is 4 years, its south pole could be very cold. And imagine if you had an impact upon it, then the south pole would just shatter like glass into shards. And so possibly in my most fantastical dreams, we would see both the south and the north pole of Psyche being a mixture of shattered shards and ductile impacts, and its equatorial regions all more ductile impacts. And that would give us really great limitations on the science, on the surface temperature. So there are some little ideas. Rona, I don't know if you had anything to add to that, or that was, yeah.
That sounds absolutely wild. Let's hope it lives up to that dream.
I know. I worry it's going to be boring in the end. Is that possible? I hope not.
I don't think so by the sounds of it. Maybe let's take a final question, if that's okay with you guys, as we're kind of at time now. Is there a minimum size of metal core before a dynamo forms? And does it depend on the rotation speed of the asteroid?
Yeah, go ahead, Rona. That's right in your wheelhouse, right?
Okay. So that's actually an open question. We don't know how small you can go before you don't have enough energy to create a dynamo. So the dynamo is created because there's enough thermal gradients for convection motion of the metallic materials in the core. So for if you take a naive extrapolation from what we know about the dynamos of the Earth, and you extrapolate it even to the moon, which is smaller than the Earth, but not as small as an asteroid, you already run into difficulties of saying, like, how come did the moon actually generate a strong enough magnetic field to explain the magnetic field we see in Apollo samples? So even the moon is challenging for us to understand how it created a dynamo. There's a lot of evidence that it did have a dynamo billions of years ago, but we cannot explain the paleo-intensities that we infer from the measurements. So, and then when you go to down to the realm of asteroids, and I think that's why Linda said their paper was controversial about the partial differentiation, and the idea that the magnetization that you see in chondrite meteorites comes from a core dynamo of an asteroid is still controversial. So there is no lower limit. I don't think anyone proved that you cannot have a dynamo, but you can also, nobody proved that you can in such a small body. So this is an open question. And for the rotation may play a role. Like for the moon, for example, there are some models that suggest that maybe the precession of the moon or maybe other changes in its motion kind of gave that extra energy that you need to crank up a stronger dynamo, but that's also still an open question. So we don't have that many dynamos to explore, right? We don't have that many examples. We have the Earth, we have Mercury, we have Ganymede, and then we have the gas giants, which are completely different animals. So if you look at terrestrial planets, we have very little to explore. So Psyche is kind of an end member of that as well. So I think that's also what makes it so exciting and informative to like fill in all these gaps.
Cool. Yeah, exciting to hear there are magnetic mysteries close to home and far away as well. I said that was the last question, but maybe if you'll indulge, I'd really like to ask this question that's come in from Laura Stevens, which is relating to the first bit of the talk. How can we divorce our attachment to the hero model in hiring, promotion, grant funding decisions within science?
Yeah. Well, so this is such a great question, and it's kind of the key question of our age is how do we overcome our implicit bias? Because every single one of us is making judgments, of course, as is famously discussed constantly these days. And so it's really, really hard to completely eliminate all of the information about a person when they're applying for a grant or postdoctoral fellowship or something. You can eliminate their name, but you can't actually eliminate where they studied or who their advisor was or the people they write papers with. There's so many things we have bias about immediately. So one process that is hopeful is a kind of a reminder process. So it's been shown that that the words that we hear or read right before we review something or take a test are very influential on our thinking. For example, there are these studies that show that if you have a group of girls in a room getting ready to take a math test and someone randomly comments, the instructor randomly comments, you know, girls are just not very good at math, their scores are much lower than if someone just randomly comments like everyone's going to do great today. It actually has a huge influence on us, even though we'd like to think it doesn't. And so a little self-reflection question before you start your review process, reminding you about implicit bias and reminding you, you know, how to read adjectives when people write about people or how to interpret people's letters. That is promising as a way to have us tamp down our implicit bias. And of course, using rubrics is really important. But then what about just talking about it like we are right now? What about if we just occasionally bring up the fact that every single person on the team, no matter what their sex or gender or ethnicity or religion or anything is, has something important to contribute and we should listen to them. And just asserting that from time to time, particularly from leadership, has a huge influence as well. So, but share, if you've got great things, if you've got great ways to do this, we should share them.
Thanks so much for the answer to that and to bringing it into the series as well, that discussion. So
and also, I would like to also contribute to that because I think it's such an important issue. And I think I totally agree with everything Lindy said. And I think the model of the Psyche team and how it's created is like a great example. And I think it's very inspiring to all of us. And I think it shows the power of example. Like when you say, when you're part of a team that the team leader explicitly say, like, we don't condone such behaviors, we don't, you know, it's very powerful. And I think it's up to all of us as we advance in our careers to also do that to people coming behind us. And I think speaking candidly about your career, speaking candidly about dilemmas that you had, that not everything was nice and smooth and you knew exactly where you're going to be 20 years from now. I think that's really, really important because I think that plays into that hero model, that like you look at somebody's career when they show up in a seminar, they're like, I've been doing this for 30 years. And you're like, oh, this person is like that. And it's like, you don't know who you are going to be in 30 years. And I think that uncertainty and that doubt is so integral to who we are as people. And I think it's really important to not play into that myth that everybody has everything figured out. And
yeah, fantastic. Thank you. Completely agree with those sentiments. I just want to say thank you so much again to our speakers today for covering some fantastic science and some fantastic thoughts on science as well. Our next talk will be in 2 weeks' time from Barbara Sherwood-Loller on the 11th of February on the hidden hydrogeosphere, implications for deep subsurface microbiology and the search for life. So thank you everyone for joining us. Thank you, Lindy and Rona. Take care, everyone. See you again.